Hello, everybody. So let me share my screen with all of you. So in this recorded session, I am going to complete the remaining part of chapter number 4. So last session, I finished discussing all these three assumptions. Now I start from this new topic. So now we know how to estimate beta naught cap and beta 1 cap, and these are the estimators of the population parameters, beta naught and beta 1. So, we when we calculated this beta naught cap and beta 1 cap using only one sample, but we could have drawn so many other sample as well. So in the population, we can draw not just one sample, but several many samples, right? So if we draw other sample of same size and we estimate this beta naught cap and beta 1 cap, they're not going to be the same because the sample values are different. And therefore, since we draw sample randomly, therefore the values for beta naught cap and beta 1 cap are random variables. So now they become random variables. Why? Because we are drawing samples randomly and we then calculate using a random sample. So basically beta naught cap and beta 1 cap, we have a whole sampling distribution. We have a whole sampling distribution of beta naught cap and beta 1 cap. And these are the estimates of beta naught and beta 1. Now suppose we are not going to take all exhaustive samples, okay? But if we had taken all samples and we had calculated or estimated beta naught cap and beta 1 cap, and if we take the average, the expected value of beta naught cap, and if we take the average value of beta 1 cap, beta naught cap and beta 1 cap, then we get the population parameter basically. So that is the what we call that when estimators are unbiased, then this property must hold. That is, you have different, oh, sorry. So, so you have different beta naught for each sample. And if you take the average, that average actually, the expected value is exactly equal to the population parameter beta naught that you have not estimated, or you don't know the value of beta naught, you estimate it. And similarly, if you have all beta 1 cap, and if you take the expected value, that will give you beta 1. If this is the case, then we say that our estimates are unbiased. So beta naught cap and beta 1 cap are unbiased estimators of beta naught and beta 1. And we can prove that this is true. So this is the derivation. It looks a bit complicated, but let me explain this. We have already shown you when we calculated in the last recorded session that beta 1 cap is n sigma xi yi minus sigma xi sigma yi divided by n sigma xi square minus sigma xi whole square. Or you can write this formula as well: sigma x minus x bar yi minus y bar divided by xi minus x bar whole square. You can also write this, that is, this xi minus x bar is a small xi, and this is a small yi divided by xi square. Now in the previous recorded session, I showed that this formula can also be written by just replacing this small yi to capital yi. You can do this, right? And I showed you that when you take the yi as yi minus y bar, and you open multiply with xi and then open the bracket basically, then you end up with this formula. So this is exactly, all these four formulas are identical technically. Okay. Now let's assume that ki, in chapter 4 they have used different terminologies, but doesn't matter if you know the concepts. So suppose ki is equal to this xi divided by sigma xi squared. Remember, these are all small xi's, right? So what I'm basically saying, that let me show you here so that you understand what I'm trying to show you. What I'm doing actually, once I know this beta 1, right? Once I know this beta 1, then I am just assuming that this xi, this whole thing is ki. Okay. So this is ki, that is xi divided by sigma xi squared. Now ki has certain characteristics. And let's do the characteristics. Number one, if you take the summation ki, that if you add ki up to all n observation, the answer is 0. If you take sigma ki square, the answer is 1 over sigma xi square. If you take sigma ki xi, then the answer is 1. And I have derived everything here. You can see what is sigma ki. If ki equal to this, and if you want to calculate sigma, then you have to put sigma here. So, and you know that sigma xi is always equal to 0. I told you that when you take this x minus x bar, this is always equal to 0. The moment you put sigma here, this term is 0. Doesn't matter whatever be in the denominator. So this is equal to 0. That is what I said. Sigma ki square. So sigma ki square is sigma xi square, because this is only x. So you just multiply by x, xi square, and this is xi 4, because 2 2s are 4, right? Because you're taking the square. So this will cancel. So you get 1 over sigma xi square. And similarly, sigma ki xi. So sigma ki xi, sigma, this is k, and this sigma is here, sigma ki multiplied by x. So sigma xi square, and in the denominator you have sigma xi square, so they will cancel both of them, and you get one answer, right? So these are the characteristics. Why I'm doing this? Because we need this when we derive these two unbiased properties. Now let's first write the notice. In this model, I did not put a cap on beta naught and beta 1. And that is why I wrote here population regression function. So that is population regression function without any cap. And we want to estimate this beta 1 with using beta 1 cap. And the formula, you know that this is the formula that we just showed you earlier. We put xi over sigma xi square as k. So I can write this as sigma ki yi. Now notice one thing, that beta 1 cap, that is this variable, is a linear estimator of y. Why is linear? Because you don't have y square here. So you have just plain y. So it's a linear function of y. Let me put this way. Okay. Now we do further. We continue by doing this. Instead of yi, I can put the value of the whole this yi here. So sigma ki beta naught plus beta 1 xi plus ui. And then I apply this sigma sign. So beta naught sigma ki plus beta 1 sigma ki xi plus sigma ki ui. And I've already shown you that sigma ki equal to 0. So this term is gone. Similarly, I showed you that sigma ki xi is equal to 1. So I have only beta 1, that is here, beta 1. And then I have this term sigma ki ui. Okay. Now I apply expected expectation. I take the average. So expected of beta 1 cap is equal to beta 1 because it's a constant number, beta 1, it's constant number, plus sigma ki, and I apply expected ui here. Why? Because it says x is non-stochastic. Okay. X, K is what? I showed you K. Let's see this. In K, you have all X. Right? And X is not a random variable, right? So X is non-stochastic. We will discuss this non-stochastic, sorry, in later chapters, right? I think in chapter number 15. Uh, So sigma, that's why we take K out of the expected sign, expected UI. I have already shown this is one of the assumption, if you remember, that expected UI equal to 0 by assumption. So this whole term is gone. And I prove that expected beta 1 cap is equal to beta 1. That is, beta 1 cap is the unbiased estimator of beta 1. Similarly, I can also prove that expected beta naught cap is equal to beta naught by using this equation. You know this. This is the first partial derivative when we take the sum of squared error, and we take the first partial derivative with respect to beta naught, and we found this equation beta naught equal to y bar minus beta 1 x bar. Just take the expected sign on both sides. So expected here, and then instead of so expected. Now, what you are doing basically, so instead of y, what is y bar? So I derive y bar here. So see, this is the same equation here. So if I take the y bar here, that is beta naught plus beta 1 x bar plus 1 over n sigma ui. That is the ui bar, but normally we write sigma ui 1 over n. So I write all this here, and then this term minus beta 1 x bar, this term is here. Okay. And then from here, go to here directly. Right. So expected beta naught equal to this beta naught is here. Then plus apply expected sign. This is x bar and this is also x bar. I take x bar common. And this is non-stochastic, it's a constant number. And we apply expected beta 1 minus beta 1 cap. So beta 1 minus beta 1 cap is this. This is beta 1 and this is minus beta 1 cap plus 1 over n u sigma ui. We know that sigma ui equal to 0 or average is 0, right? Expected ui equal to 0 because of the assumption. So this term is gone totally. And I know from here that expected beta 1 cap is equal to actually beta 1. So expected beta 1 cap minus beta 1 is equal to 0. So this is equal to 0 as well. And when this is 0 multiplied by x bar, the whole term is 0. What we get, expected beta naught cap is equal to beta naught. That is, beta naught cap is the unbiased estimator of beta naught. Okay. These are few formulas. If you want to just go through it from the textbook, that is fine, but we are not going to use. Now, some additional algebraic facts about ordinary least square. So when we use OLS method, when we estimate beta naught cap and beta 1 cap by minimizing the least squared error, that is what we call ordinary least square method. When we do this, then these are some of the facts. Number one, the expected value of ui, that is 1 over n sigma I equal to 1 to n ui cap is always equal to 0. And this is the derivation. So you know that ui cap is yi minus beta naught cap minus beta 1 cap xi. And then you just instead of for beta naught cap, you just write y bar minus beta 1 bar X bar. We have done so many times, and you solve. Then I told you that any variable, when you subtract from its mean and add, it's equal to 0. So this is also 0, this is also 0. So sigma ui equal to 0. Again, I don't have to show, you should be able to. I have given you the derivation. If you don't understand, you know my phone number, right? It's 587-998-7779. Just give me a call. Oh, text me. Sorry, don't call me. Just text. You can call me, but sometimes I'm unable to pick your call up. So just text me and then I will respond right away. So similarly, the average of y estimated value is the sample mean. And that is true. That is, when you have estimated all values, y bar, that is on the line, and when you take the average will, it means your regression line must pass through y bar. And you can see from this equation, because you remember, this is beta naught equal to y bar minus beta 1 cap x bar. So basically, this line is passing through y bar and x bar. Okay. So this is the derivation. You can do it your own. Similarly, third is sigma ui cap xi must also be equal to 0. I have shown you the derivation, and this is really easy. Only one um, hint here. Everything is straightforward up to this point, because once you get this beta 1 cap, then you have to put the value of this beta 1 cap that we derived earlier, and you put the value of beta 1 cap, and then you will get the answer. Okay, so you'll get the answer, that is 0. And similarly, I have already shown you that R square is basically, this is the formula for R square. R square is basically ESS divided by TSS, explained sum of a square divided by total sum of a square. So basically, your total sum of a square is equal to sum of a square error, that is unexplained and explained. So here we showed you, that this is the case, right? So if you calculate, oh, sorry. So, so if you calculate TSS, right? The total sum of square is this, and then we derive everything, and then we end up with these two, with this sigma ui. I can't write here, right? So basically, what you get, this term is equal to 0, and you are I can, and you can get this same thing. Okay, so basically, I'm showing you here that this sigma ui cap y bar is equal to 0. How do I know? So I just give you the proof here, right? So that is all as far as chapter number 4 is concerned. Let me show you one last thing on your course website, and then I will stop here. So this is your course website. If I go to this is, I've done okay, so week 3 and 4. So you'll be from next week, right? Will be your week number 3. And in these 2 weeks, I'll cover chapter number 4. So I've already uploaded PowerPoint slides for chapter 4 provided by the publisher. And this the lecture PPT, exactly the same PowerPoint slide that I showed you in the recording. Homework is already given here. Solution to homework assignment is given here. I have attached 3 data sets: auto, growth, and earning and heights. So I will use student test score, that is student performance, and class size, that data set as well, in my next recorded session for same chapter, that is chapter number 4. Make sure you go through these homework questions. Don't look at the solution, first solve the question. So let me open this file and take just 5 minutes to So when the estimated slope coefficient, the simple regression model beta 1 cap is 0, then what is the value of R square, right? So these are multiple choice questions. Make sure you answer them. If you don't know, you can see the solution. I have given you some derivations as well. Show that ESS is equal to beta 1 cap. And I've given you the hint, use the value of beta naught cap. And this is another, another derivation that you should be able to do it. If not, then just see the solution. Now I've given you important topics for quiz number 1 that you will be writing after week number 4. Okay, that is after finishing chapter number 4. This is from chapter number 4. So definition of a binary variable. By binary variable, I mean when you have only two values, 0 or 1. We have discussed this in the review session as well. Definition of regression slope coefficient. We discussed this in the previous recorded session, last recorded session. The difference between PRF and SRF. PRF is population regression function, that is beta naught plus beta 1 xi. Sample regression function, that is beta naught cap plus beta 1 cap xi. That is the difference. Calculate the value of the slope coefficient given the change in x and y variables. So you are given different values for x and y and should be able to calculate the beta 1 cap. If you have difficulty, always text me or email me. What is the difference between beta 1 and beta 1 cap? You know now, right? Beta 1 is the coefficient of the whole population regression function, right? This is for the sample. What is the least square objective function? You just go and see in the recorded session that yi minus whatever whole square, right? What is the goodness of fit of your regression line? That is R square. And what is the formula? Explained sum of square divided by total sum of square, or 1 minus unexplained sum of square, which we call sum of squared errors, and divided by total sum of square. So make sure go through these questions and make sure that you know all these important 7 topics in order to score 100% marks in your quiz number 1. So that's all as far as chapter number 4 is concerned. What I'm going to do next, I will upload another recorded session about how to read data using Stata, how to import Excel file using Stata software, or how to open the Stata data file. So import is easy. If you have the Excel sheet, you can easily import into your Stata software. And then I'll show you how to run basic regression, that is with only one independent variable. And we just discuss, of course, you have the whole results, but we'll only discuss slope and intercept coefficients and the value of R square. That is the coefficient of determination or goodness of fit. So let me stop here and I will record another session very soon. So I am just let me stop sharing my screen. And now I am going to stop recording. So thank you so much. Take care. Bye-bye.